All right, so yesterday, or rather the last lecture, we were talking about graph traversals. Specifically, we were discussing breadth first search. And so today what I want to do is I want to talk a little bit more about an application of breadth first search. But maybe before that, let's revisit what we did the last lecture. So you recall that we discussed the actual code for breadth first search, where we use a queue to traverse the vertices. And what was important was we first stated the breadth first search theorem, which says that when breadth first search terminates, essentially the visited vertices, only the vertices in the connected component are visited. And importantly, the path in reverse from V to S that is obtained by following the predecessor pointers. This is essentially following the tree that is outputted by BFS at S. That is a shortest path tree, right? And we discussed that when you run BFS on the whole graph, you get a collection of trees. This is called the BFS forest, such that each tree is a shortest path tree from the root, and there is a separate tree for every connected component. What I wanted to do was, and what we did last time was to discuss how would you prove such a theorem. So to prove this theorem, one first has to discover the loop invariant of breadth first search. And the loop invariant of BFS was, went through a few misses, but finally we stated this lemma, which states that after some number of runs of the while loop, let D be the distance of the head of the queue and D prime be the distance of the tail of the queue, right? So you recall that when you look at the actual queue, so where is that figure that I have over here? So when you had the DFS queue, you could look at the distance of the head. By distance, I always mean distance from the source, S vertex. And then you can look at the distance of the tail, again from the source vertex. And so this was D, and the latter was D prime. So we said that D prime will always be either D or D plus 1. The queue will always be sorted by distance. By always, I should mean at the beginning of the while loop. All the vertices that have been DQ'd have distance at most D, and all the vertices that are not visited have distance at least D plus 1. This was the BFS loop invariant. Any questions at this point? Now, I'm happy to go over any of this again if there is some confusion. Okay. Now, what I said is I'm going to make this an exercise, although I will discuss, I'll give some discussion on how to prove this. Excuse me. But let us actually argue that the BFS, starting from a source, outputs a shortest path tree given the loop invariant. And this proof can be done essentially by using the loop invariant to argue that when you look at a vertex V, okay, so maybe let me make this more, let me make this more precise. So we want to prove that BFSS outputs a shortest path tree. We will prove this by induction on the number of visited vertices. The base case is trivial, because in this case, there's only one. When you look at the base case, we say there's only one visited vertex, and that's S, and the distance of S to itself is 0, and it's the root of the tree. So no problem there. For the induction step, consider V, which is the next vertex that is visited. So that's V. And let D be the distance of the DQ'd vertex. So V is visited because it is the neighbor of a DQ'd vertex, and call that vertex U. So U is the head of the queue. It got DQ'd, and V is an unvisited neighbor of U, and so V will get visited. Now remember, by induction, there's already a shortest path to U. That's the induction that we're doing on the number of visited vertices. So U is already visited, there's already a shortest path to U. And we need to argue that that shortest path with this edge will be a correct shortest path. So let me draw a little picture here to maybe explain this better. Sorry, turned a bit. So I'm going to draw some pictures here, and then I can go back to what I've written. Okay, what is the situation? So here is our graph. Here is V. U was already visited. And we said here there's this edge. And so maybe there's some set of, this is the set of visited vertices here. And so at this point, we also have some current tree. This is whatever tree has been constructed thus far. And so U is already present in the tree. What we know by induction is this is the shortest path. Right? This is by the induction hypothesis. What we also know is that V is going to get attached over here, right? Because V is the neighbor of U. And so what we need to argue, or we need to answer this question, why is a shortest path from S to U with like plus the edge UV. Why is this entire construct here, why is this a shortest path from S to V? This is what we need to answer. We need to find out, because if we can answer this question, then we would have completed the induction. This make sense? Okay, so, go ahead.
Why aren't we proving that the shortest path is from S to U? Because we already proved that, and now we are like moving forward where we need to further prove if there is a shortest path from U backwards to S, then there should also be a shortest path from V backward to S, because V is connected to U. Is this what we're trying to prove?
So, okay, what we're trying to prove is that BFS outputs a shortest path tree.
So then we should prove that there's a shortest path between U and S, right?
But this we know by induction. We're doing induction on the number of visited vertices.
Mm-hmm.
So at any intermediate stage, assume that all the information has been computed correctly. Let's prove that the next is also computed correctly. The induction is on the number of visited vertices.
Okay, so like in the intermediate stages, we just assume that it's proved. But for the final state, we need to prove that.
It's not just the yeah. Well, I mean, but you know, how does induction work, right? Induction says you make an induction hypothesis, right? And okay, so maybe let me write this out in a little bit more detail, and then maybe this will answer your question. So I'm going to write various things. I'll come back to this.
Okay, sure.
So maybe I'll let me use a separate page for this. Okay. So what is the induction? What is the statement? Okay, I'm going to make a statement here, and I'll say that BFS S. So I'll just say that for all I less than n, BFS S correctly computes the shortest path to the first I visited vertices. This is the statement that I'm proving by induction. Observe that this is essentially not really one statement, it's a parameterized statement. There's a statement for every I. Right? So there are really n statements here where you can think of Si, the statement Si is this. And what we want to prove for all I Si So what do you do? How does induction work? Induction says, well, okay, so first you prove S, let's just say S1, which is when only one vertex is visited, but this is just the base case. And then what you want to prove.
Sorry to interrupt. So in our case, this base case is from S to U?
No, the base case is from S to itself.
Okay.
U is an arbitrary vertex. And then you want to prove Si implies Si plus 1.
Okay.
And so Si, in this case, in this example that I've given over here, implies that BFS S has computed a shortest path to U. Right? Because we're saying consider V, which is the next vertex that is visited. Let us look at how it's visited. It's visited because a vertex got dequeued. That vertex is already visited. And by the induction hypothesis, BFSS has already computed a shortest path to that vertex.
Yeah, okay.
Does that make sense?
Yeah.
Yeah.
There's a comment in the chat. So I find it a little hard to manage the chat. So, let me see if I can pull up the comment. If you are trying to do strong induction, well, this is in some sense the way that I've written this statement. Strong induction and weak induction are equivalent here. Because to assume that this statement, observe that Si implies Si minus 1, the way it's written. Because I look at the first I visited vertices. So I'm actually doing strong induction over here. But if you want to be more, this is really a technicality. I am doing strong induction. Don't get hung up about strong versus weak induction. This is really not an issue. Think of it in terms of there's a particular statement you're trying to prove. And this statement is parameterized by all vertices. Think of you're understanding this process. You're saying the process up to a point is doing the right thing. Then the process should do the right thing at the next step. Eventually, this implies that the process will be finally correct.
That makes sense. Thank you.
Yeah? Okay. All right. Any other questions about this? Does this make sense? Okay.
One small question.
Yeah, go ahead.
If we're going to use this assumption for U, why can't we use the same assumption for V? Why do we have to prove that?
Because V is not yet visited.
Okay, got it.
Right? So you're saying now consider the next vertex that's visited.
All right, got it.
To draw a picture, what you know is that BFS has correctly found the shortest path for all the vertices in the shaded region. Now, when the next vertex enters the shaded region, you want to say it computes the shortest path to that correctly, assuming it has a shortest path to everything in the shaded region.
Right, but we're making the same assumption for all the previous nodes. Huh?
You're doing induction, I guess, is the only way that is the way that I can put it. Isn't that what induction is? Induction says that you make the assumption for all the visited vertices, that this is done correctly. And so, if you can, using that assumption, argue that the next visited vertex is going to have a shortest path, then using the principle of induction, this must compute the shortest path everywhere.
Right.
Maybe another way of saying this is like, okay, if you know that it has computed the shortest path for the first 10 visited vertices, can you at least argue that it's going to compute the shortest path for the 11th visited vertex? So I'm not assuming that it has a shortest path for the 11th visited vertex. I'm only assuming it has a shortest path for the 10th visited vertex, or every vertex up to the 10th.
Okay, now I got it. So the point is that you need to, you assume that for the first 10 vertices, it computed the shortest path. And by using that assumption, you're proving that the 11th one was the shortest. And if you're able to prove that, it means that the previous 10 were also the shortest.
No, that is not correct.
Oh, that's not correct.
You are not you cannot. Okay, so this is about induction, right? When you're proving that SI implies SI plus 1, this does not say anything about the truth of SI. You're merely proving an implication. You're saying if SI is true, then SI plus 1 is true.
Yep.
So this statement, SI implies SI plus 1, says nothing about the truth of SI, nor about the truth of SI plus 1 as is. It is only an implication. But what you say is you can chain all the implications together because the base case is true. S1 is true implies S2 is true. S2 is true implies S3 is true. And so on and so forth, so everything is true.
Okay.
Yes, no, it's a little hard to judge on Zoom whether people are following or not.
Yeah, so the only fact that we know is that the base case is true, and we build on from that.
So this is, what is induction? Induction says you have a family of statements parameterized with all natural numbers, and you want to prove that all those statements are true. And induction is a mechanism to prove it. Induction says, okay, if you can prove that the first statement is true, and if you can prove that the ith statement implies the I plus third statement, then the principle of induction says this implies that everything is true. All statements are true.
Yeah, that makes sense.
Right? So what you need to do is prove an implication. You are not proving SI, nor are you proving SI explicitly. You're proving them as an implication. You're essentially proving every statement through a chain of implications, but you're not going to write out, I'm going to do the chain of implications each time. Right? So, but this is very important because essentially all proofs regarding algorithms and data structures are basically induction. Because you're trying to argue about the size of this object, but you don't know what the size of the object is, right? Just like your graph, you're saying there are n vertices. What is n? N is a parameter. So any proof essentially goes via induction. And this is what induction is. Like what I've written here, that's induction. This is your base case. This is the induction step. The induction step is an implication. I want to emphasize that it's an implication. Like in the context of BFS, we're saying, suppose everything visited so far has been computed correctly. The shortest paths have been computed correctly. Then the next shortest path will be correct. But you can say, how do you know that it's done the previous ones correctly? And I say, I don't know. I'm merely proving an implication. I'm saying, suppose it was correct, then the next one is correct. The way that you argue all of these are correct is by following the chain of implications of the previous induction hypothesis and so on and so forth. But one doesn't explicitly write all that. One says, this is a proof by induction. This is like a principle of logic.
Yes, but like in the end, we're trying to prove it for the all cases, right? That like every time the BFS traverses an algorithm, the graph, a path from the source to any vertex is the shortest path. That's what we are trying to prove.
You're trying to prove this statement here, the one that I've written here, right?
Mm-hmm.
You see that there is a for all I less than n, right?
Yeah.
So technically, one can interpret this as actually a set of statements. It's a set of n statements.
Yes.
And what you're really interested in is you're interested in the last statement. Because if I do the last statement for n, then n visited vertices implies everything.
Yep.
So I want the last statement, and the way I prove the last statement is I prove the first statement, and then I prove that the ith statement implies the I plus first statement. And this is enough to be a proof of the last statement. Yes?
Yeah. So proving an arbitrary ith and assuming it's true, and then showing that the ith plus one statement is true, we can say that for any arbitrary statement, for any arbitrary I, since we can prove I plus one is true, we can say that for any statement, and thus proving the whole set.
Essentially, I mean, what you're restating is the principle of induction.
Okay.
Right? What you just stated here is the principle of induction. The principle of induction says that when you prove S1 and you prove Si implies Si plus 1, this constitutes a proof of everything. Yeah, so at this point, I want to answer any questions or any doubts you have about this approach that I'm following.
Professor, I want to see how you're going to use the base case in the induction step. Like, you're saying like it's implied that Si or Si is plus 1 is going to be the induction step, but how are you going to use the base case? I'm confused in here.
This is the principle of induction, right? So, okay, so the question is, if you have this, how do you prove S10? Why is let's say S5 true?
No, why plus 1 is correct, or why?
Because you're going from one statement to the next.
Okay, I thought, yeah, I mean, I had this in mind, the weak induction, which is -1, the one before is correct, and then the current one is correct.
Sure, okay, so you can do Si minus 1 implies Si.
Okay.
Sure, but that's just renumbering I to I minus 1.
Okay. Then it's the same.
It's the same thing, right?
Mhm.
I mean, I could prove that Si minus 3 implies Si minus 2. It's basically the same thing. It's like I'm just relabeling. It's like reindexing something, relabeling something. That doesn't change the statement itself.
Correct. Okay. Thank you.
Questions? Okay. So far, so good. Shall we continue?
Yes.
All right. Now let us come to the main argument we had. So we said, suppose you already have a shortest path up to U. Y is, and we know that V is visited from U. So what's going to happen is that the predecessor of V will be U. So why is this the shortest path? That's what we need to argue. We need to use the BFS invariant for that. So let's do this sort of step by step. Let D be the distance of U from S. What is the length of the path from S to V in the tree, or in this tree? What is the length of this path?
D plus 1.
Plus 1.
D plus 1. So what if we can argue? So if we can argue that the distance of V from S is actually D plus 1, then we'd be done. That would then give us the proof. Is that right? So let us show that the distance of V from S is D plus 1. Okay? And now I'm going to show you the loop invariant. And I want you to tell me, I'm going to, pause for a minute, read the loop invariant. Read the loop invariant. And the loop invariant should tell you why the distance is D plus 1. I'm going to pause for a minute and you'll read the loop invariant.
Because V is not visited and it says the fourth point says all vertices that are not visited have distance at least D plus 1.
Good. So we know that by the fourth point, we know that the distance of V from S is at least D plus 1. Good. By point 4 of the BFS loop invariant, V was not visited, U was the head of the queue, so the distance, I'll just say distance of V was at least D plus 1, was greater than or equal to D plus 1. But why is it equal to D plus 1?
Because U is the predecessor of V.
Okay, and
By
And by
0.3, yeah, at most, it should be at most 3.
at most, but at most D would then contradict this, no? You're almost
Isn't
there.
it-
Yeah.
Isn't it at most D or D plus 1, but because D we're already at distance D, it has to be D plus 1?
Good. So essentially what it's saying is, you know that this is already a shortest path from S to U. And so this is a path in the graph. And this path from S to U to V is already a path of length D plus 1. This is a path of length D plus 1. So obviously, the distance is at most D plus 1. Right? The moment you have a path of a particular length, the distance can be at most that, right? That's the shortest path distance. And therefore, the distance, it's almost, in some sense, I will say in quote, it is sort of self-evident because there is a path of length D plus 1. So the distance is at most D plus 1. And if it's at most D plus 1 and greater than D plus 1, it actually is D plus 1. So that means the distance of V from S is D plus 1, and the tree is giving you an explicit path of length D plus 1, and hence this output is correct. I will write a little bit more about this, but I want to make sure that you understood my chain of reasoning here. Okay? So I'll say that the tree has an explicit path of length D plus 1 from S to V. Why? Because the path from S to U has length D. This is the induction hypothesis. Right? And so it's obviously D plus 1. It's whatever that length is D plus 1. That's the plus 1. So the tree has an explicit path of length D plus 1 from S to V. Hence, the distance of V is at most D plus 1. So the distance of V is exactly D plus 1. So we prove this fact. And the tree has a path of this length. So the output for V is correct. We only prove the output for V is correct. But this is exactly the induction. This completes the induction. So the induction is done at this point. Okay, so I've sort of expanded out on what I wrote earlier. So what I did sort of in the last 5 minutes in the previous lecture, which is a bad idea, but I said the induction is we're doing induction on the number of visited vertices. The base case, you just argue about the root. And the induction step is what I wrote over here. And so by this argument here, we complete the induction and BFS is correct. Any questions about this?
Would it also be necessary to say that we can show this? The only way to really contradict this statement is that the Q contains at most 2 vertices with that have distance like at least 1 apart from each other. And if the head of the queue and the end of the queue was distance 2 from each other, then it would contradict this statement.
Well, I mean, but you're right. Well, yes, you're right that would probably be a contradiction. But I mean, I think you should think of it differently. You should think of it as you first prove the loop invariant, and then you use the loop invariant to imply the statement. What you're saying is that hence if the loop invariant was gone.
The only reason I bring this up is because I don't know if the loop invariant kind of implies that the queue has the distance of at most 1 from every element.
It's written here, right? Because it says that the tail of the queue is distance. The tail of the queue has distance d or d plus 1.
Oh, okay. Okay.
The loop
Then I guess
invariant
it's
contains
implied.
that. Yeah, it's implied.
Okay.
Yeah. The loop invariant contains that.
So,
Although, as was pointed out, this was the only part of the loop invariant that you needed. But to prove this, you're going to need all of these.
Do you also use induction to prove the loop invariant?
Yes, you will use induction over the number of steps of the loop, over the number of the steps of the while loop.
Perfect.
Exactly. Yes, it's a lot of induction. Essentially, all proofs in graph theory. This is essentially like a proof in graph theory and graph algorithms. It's all lots of induction because you're arguing about a discrete structure.
I know you said not to focus on the difference between weak and strong induction, but
Yes.
I think that's the only thing I still don't quite understand. I assume that's something I should look into on my own time.
Well, I mean, my point is, I think that that sort of distinction is not going to be as important for the kinds of proofs that you're doing, because mostly what you will be doing is strong induction. Think of it this way, right? So you have a particular process like BFS, and you want to argue that the process at the end has the right answer. So what you do is you say, well, if I could just argue that the process is doing the right thing at every intermediate step, that's enough. And so your assumption becomes after so many, let's say after I steps of the process, the output has a particular state. And you want to argue that at the I plus first step, it is updating the output correctly. This is in some sense a strong induction because you're assuming that everything before that point was correct, not just that the ith step was correct. Does that make sense?
That does make sense, actually. Yeah.
So it's kind of like in this picture here. You are right that the only thing that you needed was that there was a shortest path to U that was the predecessor of V. We don't actually use the fact that there were these other paths which are also correct. But how do you make such an assumption? It's because a priori, when you start at V, then you realize that you only need a shortest path to U. So it's a lot easier to say that after it visits I vertices, all the paths to those vertices are correct. Not just the vertex that you need, because you don't know how to specify the vertex that you need before you actually start the proof. Does that answer your question? So effectively, it's strong induction.
Yeah, I think that does answer my question. Thank you.
Yeah. I mean, and I want to emphasize that proofs by induction, this requires a lot of practice. It requires a lot of writing. But I guarantee you, when you do this, your thinking will become so clear. You will be able to reason about processes very clearly when you think in these terms. Actually, I have a question. How many of you have written code in a functional programming language? So A is I've written code in a functional programming languages. B is I have not. Okay, so it's about 70% of the people have written code in functional programming languages. This is good. So a functional programming language, when you write the code, it's essentially you're writing a proof by induction. Induction and recursion are basically the same thing. So another way of thinking about this is think of it procedurally. You want the shortest path to V. If you have the shortest paths to all of these, then you extend it. And that's sort of how recursion works, right? But recursion says, assume that when you make the recursive calls are all correct, then build the solution. And this is in some sense exactly the same thing. Recursion and induction are really two faces of the same coin. Recursion is what you use in code, and induction is what you use in a mathematical proof. Okay, any questions?
Yeah, just one thing. So when we are writing out a formal proof of this, right, or any proof for that matter that uses a loop invariant. So did you say that we are also required to sort of prove all the steps of the invariant? For example, the first step here, are we also required to prove all the steps?
Well, I mean, yes, your exercise I'm going to give you is to prove the loop invariant. What we did over here is to use the loop invariant to prove something else. So usually I will kind of specify that, look, if there is something that I have already proven in class, you can use that statement. You don't need to reprove it from scratch.
Okay.
It's kind of like code, right? When someone builds a library, then you don't go and rebuild the library. So think of like all these theorems are like various parts of a library that we're building. And these are the tools that you will use to prove more things, which is like libraries are tools that you use to write more code.
Okay, so we have proved that the BFS, it outputs the shortest path tree when it terminates. But what we are required to do maybe in an exercise is to prove the loop invariant.
Right. So what we have done so far is to prove, we have proved that the BFS is giving the right output, assuming the loop invariant.
Yeah, got it.
And so I want to now tell you, like, how are you going to actually prove the loop invariant? In which case, then you have the complete proof.
Yeah,
right?
That makes sense.
I had one question.
Go ahead. Yeah.
So why is it called a loop invariant? Like, what is the meaning of the phrase?
Good question. So you understand what loop means because there's a while loop, right?
Right.
This is the invariant, which means that it is always true. Invariant is something that is always true. And this is always true at the beginning of the loop.
I see.
Right? Like this, like all of these statements, they are always true at the beginning of the loop. And that is what it means to be a loop invariant.
Professor, only at the beginning or during all the
So it is,
iterations?
again, I think, and we discussed a bit of this last time. So the statements made here are only true. Okay, so maybe I should be clear. What do I mean at the beginning of the loop? I don't mean before the loop begins. I mean that the loop has iterations. At the beginning of every iteration, this is true. So maybe I should say that so that's why I said after I runs of the while loop, at any stage, the beginning of step 3, remember step 3 is executed over and over again. Right? The execution of the code, step 3 is executed repeatedly.
Clear enough.
Does that make sense? So maybe I can also state over here, at the beginning of every iteration. So it is a statement that is true at the beginning of every iteration, regardless of which iteration it is. Hence, it is invariant in terms of the iteration. And that's why it's called a loop invariant. In some sense, you may not know this, but if you really think about it, every single piece of code that you write that has a loop, the only way to argue it's correct is a loop invariant. And you're already doing this mentally when you write the code correctly, except you don't verbalize it in this form. Because what do you argue when you write a code that has a loop? You're saying, okay, I'm going to keep making some updates so that in the end, the whole loop will do something correct. And so it's doing some intermediate processing at each iteration. Right? Think of something as simple as computing the factorial using a loop. You say, well, okay, if I can compute n minus 1 factorial, then I can compute n factorial by multiplying n minus 1 factorial with n. And so you can either think of it as a recursion or you can think of it as an iteration. It's all the same thing. And there's a loop invariant. Your loop invariant is after I runs of the loop, you have I factorial. If you think about sorting is also based on loop invariance. All right. Questions?
Just like a question regarding loop invariant. So like the opposite of loop invariant would be a process which could possibly be wrong in the intermediate steps, but it ends up with the correct answer.
Well, yeah, hypothetically. But then to argue that it actually ends up with the correct answer, if you wanted to prove that, then there must be some intermediate computation that is correct. So it just has a different invariant than, or rather, okay, that's a complicated discussion to have, but yes, you can think of it that way, right? In some sense, the only way to argue about loops is through this. When I say the only way, the reason I say that is because you have to do induction. And when you do induction, you need an induction hypothesis. And that induction hypothesis actually is your loop invariant.
I see.
Right? The moment you're doing induction, that is already an invariant, because what does it mean when you're doing induction somewhere? Let's see. When you're doing induction, like this is now the invariant of BFS with respect to the number of visited vertices. Invariant is just a fancy term for a statement that is true.
Right.
So any induction is essentially positing an invariant, and then you prove that invariant through this process.
Sure.
Yeah?
Yeah.
It's a good training in logic. That's what this course is about. Okay, any other questions?
So is writing a for loop also similar to just induction?
When I say writing a for loop, what I would say is proving that a for loop gives you the correct answer is basically through a process of induction. If you were to replace the for loop by a recursive code, which you can do, right? Every code that is written through a loop can also be converted to a code that is recursive. A recursive code is essentially like a proof by induction, right? When you write recursive code, you say, oh, I'm just going to assume that the recursive call gives the right answer. I'm going to use that correct answer to get the next step.
Right.
That you're basically doing induction there.
Right.
Right. So I think that the equivalence between recursion and induction, like a recursive code and a proof by induction, and the equivalence of that to basically a loop invariant. Like this is what I'm saying is these are all different ways of looking at the same thing.
Right.
But when you're trying to argue about an algorithm that has a loop, like BFS, the way that you sort of make formal headway is to find the loop invariant. Now it's difficult to find the loop invariant. It's not obvious at all. And this is something that I will show you. Let's talk about the loop invariant. But when you try to figure out the loop invariant, that's when you start digging into what the process is doing. And that's when sort of the induction hypothesis then emerges, when you try to understand what the process is doing. Like when you look at this piece of code, it is by no means obvious that the queue is going to be sorted by distance. It is not at all obvious that the vertices that have been dq'd have at most d, and this is d plus 1, all of these things.
True.
You discover this by running a few small examples, and then you try to formalize it as a statement, then you try to prove the statement by induction, and then you try to prove the things that you care about using the statement, using this invariant.
Okay. All right. Thank you.
Does that help? Does that make sense?
Yeah.
Okay. All right. So let me talk a little bit about how you would prove the loop invariant. And, the thing is, again, what I want you to take away from this course is don't be stressed out about the assignments, right? As I said, I'm going to give you the assignments, try them out, talk to me during office hours, talk to the TA during office hours, and you can submit twice, right? You can submit something, and then the TA will give you feedback saying, well, your proof doesn't look correct here, right? So I want you to treat this as a process of you improving your formal writing, rather than this sort of like, oh, I have deadlines, I have to meet them so that I get a particular grade. And as long as you do the effort for the course, you should be fine. Okay. Now, let us talk about this loop invariant. How are we going to prove the loop invariant? And as we, wait, sorry, it's out of focus. We said we're going to prove this also by induction. By induction over what? I mean, this is going to be our induction hypothesis. You're going to say, suppose after I runs of the while loop, this is true. I want to prove that this is going to be true after the I plus 1 runs. So I'm just going to write out some of these things. So we'll say, suppose, okay, so first you need to argue the base case. But I'm not going to tell you about the base case. You'll see that the base case is the base case is obvious. Because initially, there's only one vertex in the queue. So it's obviously sorted by distance. This is obviously true because d prime is equal to d. All the vertices that have been dequeued, well, nothing's been dequeued. And everything that's visited has distance at least 1. Because initially d is 0. Right, so the base case is easy. Okay, this is easy. So now let's do the induction. So suppose the loop invariant.
Are the d's that we're talking about in the loop invariant the actual distance or the distance in the tree that we're constructing? I mean, I know that those are the same thing, but we.
That's a good point. So you can say that this is the actual distance.
Okay.
This is the actual distance because at this point we're not explicitly referencing the tree.
Sure, but
So
it seems like you would.
You don't need to. You actually don't need to talk about the tree in this invariant.
No, I'm saying it seems like if we're saying like, okay, at the next step, when we dequeue a vertex and add its neighbors, right? They're all going to be at distance d plus 1 in the tree, but showing that they're actually at distance d plus 1 in the graph might be hard because like we just showed that they're at d plus 1 in the graph using this invariant.
Yeah, so no, this has to be the tree. I'm sorry, this has to be the graph. This is the original distance. Did I say tree? This is the distance in the graph.
Okay.
This is the distance in the graph, right? So yeah, this is the distance in the graph. I don't think, let me just think about this for a second. Do you need to actually reference the tree in this proof? And you're saying you need to do that because, no, I think you'll be fine here. Let's walk through, let me just sort of sketch the argument and then we'll see. We'll see, but I think you'll be fine here. So suppose the loop invariant is true. After I iterations of the while loop. Okay, so now consider the I plus 1th iteration. Okay, so and we'll use D just as before. So this is what the queue looks like. Here is the head. And so there are some things at distance D and some things at distance D plus 1. This might be empty, right? This is going to get dequeued. And then we're going to add some stuff to the queue. That's what happens in this iteration. So this is U. It's got some neighbors. Some of the things are visited. Nothing that's visited gets added. So everything that's added, these are all not visited. So we know, this is where now, by the induction hypothesis, the distance of these vertices is at least D plus 1. But this is again similar to the argument we just made. I'm going to write out a bunch of things here and then we can discuss it. But the distance is also at most the distance to U plus 1. Right? And that's because it's a neighbor of u. So the distance is at most the distance to u plus 1. And this is equal to d plus 1. So these two imply that all the new vertices added in the queue have distance d plus 1. And these are added to the end of the queue. End of the queue. Hence the queue remains sorted. So what I've essentially done is I've proven step 2. I've also proven 1 because everything that's added is going to have distance d plus 1. Any vertex that's dq'd will have distance at most d. Why? Because what's going to get dq'd over here is distance d. And anything that was not visited will have distance at least d plus. Now you have to be a little careful. You have to do a case analysis here. Is when you dq the last vertex at distance d, the proof changes because the head of the queue now is further away. So there are two cases that you need to do here. So is this making sense here? Like I've drawn this as a picture, but then you're going to have to write this, sort of as a proof. Any questions about this?
Should we be using diagrams when doing our homework as well? Doing these proofs?
Good question. So you should be drawing diagrams in your notes. You do not need to provide them for the proof. It is an excellent idea to draw diagrams when you're doing it out. I'm not going to enforce you to put them. You're welcome to put the diagrams in. It's very hard to do all of this if you don't draw these diagrams. This is in some sense maybe an unfortunate feature of proof writing as it is. The modern proof writing is we don't actually add too many pictures and formal proofs when written in research papers or written in books, but diagrams help a lot. Any other questions? Just to get a sense, I'm just going to poll you and ask you, excuse me. Are you getting a sense of how to prove the loop invariant by induction? A is yes, B is no. Okay, good. I think most people are, the vast majority are sort of following and understanding. So, right? So I proved that it remains sorted. I'm also proving that everything added has distance d plus 1. So mostly this is fine. The problem, you'll see that your proof has to have another case where suppose this is the situation. This is all a distance d plus 1 and this is a distance d. This is when the head of the queue transitions from distance d to d plus 1. In this case, it doesn't transition. So this is like you should think of as case 1, and this is case 2. And you just write the proofs out separately for these, because things are going to change. Because the head of the queue is going to have a different distance after one loop in case 2. In case 1, d remains the same. In case 2, d becomes d plus 1. So then you have to redo all these arguments.
Well, I had one question.
Just,
whenever you DQ from the head, your distance will always change, right? Because every neighbor of u will have a distance plus 1.
That's true, but the things in the queue may still have distance 1, d. I'm sorry. They're all going to the end of the queue. The head of the queue may still have the same distance.
Oh, okay.
There was someone else who had a question as well.
What if the vertex that you just DQ'd, I guess if it's the last vertex, you're done? Or
You're done. Yeah, if the queue is empty, then this statement is sort of vacuously true.
Ah, right.
Right? So you don't have to do anything then. You can always say if it's the last vertex, then the statement is just true. Yeah. Okay, so why don't we pause here for a couple of minutes? I'm happy to answer questions, during the pause. But when we come back, then I want to talk about an application of BFS. Okay, so let's continue. And a comment that I should have made that I did not make is, and again, this is hopefully something that you've already seen so far, is, BFS runs in time O of m plus n, assuming adjacency list representations, because you're just visiting, every edge is visited, every edge is traversed, actually I should say exactly twice, once in each direction. Once in each direction. And indeed, every vertex is visited because, BFS has a loop over all vertices, right? So the full code of BFS, you loop over all vertices, so you visit all vertices, and that gives you the n. So the whole point is that BFS is efficient. And my point about doing the primer for BFS is not that, we talk about existing algorithms, but as you want, you said, how about new algorithms? What I want to show you is that BFS can be used to solve more problems. And here's a classic problem that BFS solves. And using this, we'll even prove some interesting theorems in math. So this is determining if G is bipartite. This is also called two coloring of a graph. Okay, so let me explain this. So let me first give you a definition. G is bipartite if the vertex set can be partitioned into I'll say VL and VR. It's left and right. Such that all edges go between VL and VR. Right? So just to draw a picture, this is a bipartite graph. Edges go this way. This is not allowed. No edge of this form, and that's also not allowed. All the edges have to go between VL and VR. Does this definition make sense? That's what it means for a graph to be bipartite. This is also said, called that G is two colorable, because you color the vertices. You color the vertices with two colors so that no edge is between vertices of the same color. And these are equivalent, because what you could do is you could color all of these. You could color all of these vertices, let's say black, you color all of these vertices white, and all the edges are between black vertices and white vertices. So bipartite and two colorable are basically the same thing. So this is what it means for a graph to be bipartite. Now here's your problem. Your algorithmic problem. Given a graph given G, and assuming, let's just assume it's connected, just to keep it simple. It's connected and undirected. Okay, just to keep the discussion simple. Given graph G, which is connected and undirected, determine if G is bipartite. And if so, output a valid two coloring. This is also called a bipartition. This is the problem. This question makes sense. Any questions about the question or questions about the problem?
So there's no vertices that go between, or edges that go between vertices of the same color?
Exactly.
Okay.
Note that not all graphs are two colorable. Give me an example of a graph that is not bipartite. Simple example.
K3. No.
K3.
Yeah, K3.
The triangle. That graph is not bipartite.
And like a self-loop one?
So let's assume it's simple. Good point, but simple. So no self-loops allowed. Usually when I talk about a graph, I usually mean simple, but I should have specified that. Okay. Does this make sense? So you need to determine whether this is, so this is not bipartite, but this graph, this is bipartite. Do you see that this is bipartite? Because you can color all of these vertices black. And you leave these vertices white, and this is two colorable. But you cannot do that. You cannot do that with this graph.
Professor?
Yes.
Is this the same problem as finding cycles in the graph with odd number of?
Yeah, exactly. Yeah, it's but you're jumping ahead. You're jumping ahead, but it's exactly that. Okay, good. So, does anyone have an algorithm to determine if a graph is bipartite? What's the algorithm? Any suggestions?
Did you run BFS on the graph itself to create a forest?
Okay. Then?
And then the algorithm for connecting those forests can detect if they're bipartite, I guess, maybe?
I mean, there's no forest. In this case, let's say graph G is connected. So you run BFS, you get one tree. Because if it's disconnected, then you just run the algorithm on each connected component. So the algorithm is connected. So you ran it, you got the BFS tree. Now what? Good. So, okay, so here's the graph G. You run BFS. So it's going to have some starting vertex. And there's a tree.
Oh, I meant like run BFS on the graph itself, not with the starting node. The algorithm that you should get.
Sure, but then that essentially just picks a starting node arbitrarily, right?
Okay.
Right. I mean, it basically is going to run it from every possible start vertex. It's going to pick one vertex arbitrarily, run BFS, everything gets visited, and that's it. Okay, so good. So you ran BFS and you got this.
Should we check whether like all the nodes in the BFS tree are of alternating colors?
There is no color. You have to come up with the coloring. Right? You're just given a graph. You have to determine if the graph is bipartite, and if so, output the valid two coloring. How do you determine that the graph is bipartite? Or how do you come up with the two coloring, assuming it's bipartite? Suppose it is bipartite. How do you give it two coloring?
Maybe the next node is of different color from the present node.
But when you say is of a different color, what is the color? You have to output the coloring.
I guess like the first level would be white, and then the second would be black, and then the third would be white.
Okay,
so,
good. Fine. So I got my BFS tree, and then I did this. Right? Is this a valid two coloring? I mean, there could be other edges.
I think like if we know it's bipartite.
Okay, all right, fair enough. If you know it's bipartite, then
it's a valid two coloring.
Why? Good question. Good. Good. So you're saying suppose the graph is bipartite, this is a valid two coloring. Why is that?
This is a valid two coloring.
Sorry? So, one at a time? Yeah?
Because it's in a definition?
Yeah, there's no edge between vertices of the same color.
This is only in the tree. This is not the graph. You've done a two coloring of the tree. How do you know that's a valid two coloring of the graph?
Basically, graph is an n-array tree, right?
No, the graph is not an n-array tree. You ran BFS to get the BFS tree. The graph is just something. Maybe you ran it on this. So suppose you ran BFS on this, you'll get something that looks like that. This is your BFS tree, and you went ahead and you two-colored the tree, but this is not a two-coloring of the graph because this edge is also present.
Oh, I guess it's like the tree is actually the graph. I don't know if that makes sense.
The tree is not the, I'm sorry, so you have a graph and you ran BFS to get the BFS tree. This is the BFS tree. This is the output using the predecessor array. I'm sorry, is this...
Can we use the fact that between the same colors, there's no like shortest path of length 1?
Maybe
So
just
wait. Okay, so say that again.
Between any two nodes of the same color, there is no shortest path of like length 1.
That's not true because this edge could be present. And those vertices have the same color, and there is a shortest path between them of length 1. There's actually just an edge.
Maybe just maintain distance or
But
depth to be a
bipartite,
parameter.
right?
Then this is not bipartite, right? Okay, but then, sorry, let me go back to the... Okay, so I hope this makes sense. What I've drawn here is not the graph. The graph is something. You ran BFS to get a BFS tree. There are other edges in the tree which are part of the graph.
Maybe just maintain distance parameter. Maybe check like if two nodes have the same distance from the source node.
Okay.
And then just check like if they are connected, they are not bipartitioned. Maybe if the distance are same, they are not.
Okay. All right. Good.
You don't have to worry about like there can't be any edges between nodes that are colored black and nodes that are colored white in the diagram because otherwise those nodes would be at a different depth. And then
say that again.
Well, there definitely can't be any nodes between like nodes that aren't at the same layer that are of the same color.
Good. Nodes that are not at the same layer, you cannot have this edge. That's not present.
Can we just essentially look at the distance from each node and say if it's even and it has a neighbor that also has an even distance, then it's the same color, right? Because we can use the distance as odd is one color, even is the other color.
So that's exactly what this coloring is doing. The problem is, how do you know that's a valid coloring?
So when you're adding stuff to the queue, every time you add it, you use a different color. And if the same element is getting added twice, you can check the color on that. And if the color doesn't match, then it doesn't work.
I guess
say that again. So the thing is, okay, so let me step back and say you ran BFS and you got this tree and you colored this tree. Now this gives you a potential two coloring. Now you have two problems here. One is maybe this is not a valid two coloring, even though the graph is bipartite. The second problem is Maybe the graph is not bipartite. Does that make sense? So I want to go back to previous comment, which was, I think, very interesting. It said that someone said that there is no edge that goes like this. Okay, does everyone see why that cannot happen?
That's the loop invariant, right? Where the Q cannot contain distance. The loop contains only distances in the set of D and D plus 1.
It's even more I mean, instead of looking at the loop invariant, look at the BFS theorem. The BFS theorem tells you that it's a shortest path tree. If this is a shortest path tree and there was an edge of this form, it would violate the fact that it's a shortest path tree.
Yeah, right.
Right? Because because of the distances, you know that there cannot be any edge of this form. So edges can be of what? There are only two kinds of edges. There are the edges that go from one layer to the next, and then the edges that are within a layer. So there are two kinds of edges in the tree, in the graph, I'm sorry. This is what BFS does, right? BFS says when you run BFS, in the end, you get two kinds of edges. In-layer edges and between-layer edges. Now, what happens if there is an in-layer edge? Or suppose there's an edge of this form. What happens?
Same distance, right? Like
they will have the same distance. Correct. They will have the same distance from the root.
When we get to one of the others will have already been visited.
True.
If that edge exists, doesn't it mean that it's not bipartite?
Why? Why? Good. You're right. Why?
Because then you have a connection between two nodes of the same color.
Well, right? But you're the ones who came up with the color. Maybe there's a different way of coloring things so that things are not going to be problematic.
Every tree is always going to be bipartite if you color it this way. That's so
true, but you could come up with another tree where maybe this problem doesn't exist.
Is it because it contains a cycle?
Okay, good. It contains a cycle, but cycles are bipartite. Here's a bipartite cycle. This is bipartite.
It's an odd length cycle.
It's an odd length cycle. Exactly. Yeah. It's an odd cycle. Because why is there an odd cycle? Good. So this is exactly what you need to get at, right? You need to say, if there is an edge between two vertices at the same distance from the root S. So I'll say the edge is UV. Then the cycle S to U, then the edge UV back to S, which we can get in the tree, right? So you look at the tree, you look at this path and this path. And of course, I mean, maybe it's self-intersecting, but that's okay. Or actually, if you just look at the LCA of these two vertices, you're going to end up with an odd cycle. This is a cycle of odd length, just like the triangle that was drawn. And so, let me write a claim. This is going to be an exercise. Any odd cycle is not bipartite. Right? And it should be fairly easy to see this. You can again prove this by induction. It's a good exercise. If you have an odd cycle, well, suppose it actually was bipartite, so it's two colorable. So one vertex is white, and the next has to be black, and the next one has to be white, the next one has to be black. By the time you come back, you'll be forced to color this black. And so it's not two colorable. There's an odd cycle is not bipartite. Indeed, this is part one. Part two, which is just this, is any graph that contains an odd cycle is not. Maybe I'll say two colorable instead, just so that I'll emphasize the fact that you prove this using colors, but it's the same thing. Right? So this is interesting. Whenever you have an edge within the same layer, and I'll define layer, but you basically understand this picture. When you have an edge in the same layer, then the graph is not bipartite, and BFS finds the certificate. Because BFS will find an odd cycle and say, hey, there's an odd cycle. I cannot color this with two colors.
Like, I have one question which may like deviate from what we are discussing.
Go ahead.
Like this tree, where we are joining the nodes in the same layer, how can this be possible? Because like it means that this node has two predecessors.
It has only, this is not a tree edge. This is an edge of the graph. This is a tree edge.
Yeah, but we are talking about this tree, right? So like we are joining the nodes of a tree.
We're not joining the nodes of the tree. So consider doing BFS on this graph. So let's say you did BFS. Let's say this is S. You're going to end up with this tree. Right? This is the tree that you're going to get. In this tree, if you go back to the graph and say, okay, let me look at every edge and see, does this edge go between layers or does it go within layers? You can detect that this edge goes within a layer. And the moment it goes within a layer, you can say the graph is not bipartite because you found an odd cycle.
Okay.
Does that make sense?
But that only gives you knowing that it's not bipartite. It doesn't give you the inverse of that, right?
No, it doesn't give you the converse. Good point. It doesn't give you the converse, but you'll see that the converse is going to follow quite easily. Suppose, so what we've, let me just sort of write this out. If BFS, or forget if BFS, okay, so you ran BFS. If there is an in-layer edge, G is not bipartite. Good. Suppose there is no in-layer edge. Suppose there is no edge that goes within a layer. Then what do you know?
The coloring that we came up with is valid.
Exactly, which means that if there is no in-layer edge, the coloring is valid and hence G is bipartite. If there is no in-layer edge, the two coloring of the tree, of the BFS tree, is a two coloring of G. Hence, G is bipartite. If you just stick with this for a bit, you can actually prove the following theorem. This is a theorem actually in graph theory, that G is bipartite if and only if G does not contain an odd cycle. If you think about it, that's not an easy theorem to prove by itself. But if you just run BFS, then this argument gives you the proof. Because if the graph does not have an odd cycle, then there cannot be an in-layer edge. And if there's no in-layer edge, then BFS gives you the two coloring, and hence the graph is bipartite. And if the graph is bipartite, it doesn't contain an odd cycle. Well, that's just a simple claim over here, that any graph that contains an odd cycle is not two colorable. So actually what this means is that the problem can be solved in linear time. This problem, the two coloring problem. You can determine if a graph is bipartite, and if so, output a valid two coloring in linear time. If it is not bipartite, you can provide a certificate. You can provide a proof that it's not bipartite, which is the odd cycle. Any questions about this?
So at the end of the day, your algorithm is construct the tree and then just look at every edge and check which colors are on either side of it?
Yeah, exactly.
Okay.
You can just do that, right? You can construct the BFS tree, get the two coloring of that, and then just check if it's a valid two coloring. And if it is not a valid two coloring, well, I guess there's this additional, well, I mean, not additional, but if it's not a valid two coloring, then you can actually output an odd cycle, right? By basically looking at the BFS tree. You just look at the LCA of those two nodes and that gives you an odd cycle.
Sure.
Yeah.
I guess I'm also curious if you can do this in the loop.
You can do this while you're building inside BFS as well. But in some sense, from an algorithmic standpoint, it's probably more efficient because you can terminate earlier. From a proving standpoint, it's messier. When it comes to proving the theorem, it's a lot easier just to think of BFS as a black box that outputs a tree with a particular property, right? Because then you can just use the BFS theorem rather than have to go into the loop invariant of BFS. Yeah, go on. Yes.
One question. I'm still not sure if you have to prove that you only have same layer edge, that you don't have an edge that crosses across two or more layers.
You have to argue that. No, you're right that you have to argue that no, there is no edge, but that you can prove. So I can you're right that one needs to state it more formally. There is no edge that goes between so there is no edge that skips over layers. Every edge, so edges are only of two kinds. They go within a layer or between adjacent layers. So one would have to actually state that as a claim, prove that, and then you say, okay, therefore all the edges are of in layer or between adjacent layers. Then you argue that if there is an in layer edge, the graph is not bipartite because that in layer edge gives you an odd cycle. Then you argue that if there is no in-layer edge, the two coloring is a valid two coloring because all the edges go between adjacent layers and the adjacent layers always have different colors.
So in a formal proof, you have to have a claim that, but you don't have to prove the claim.
Well, you have to prove the claim as well. You have to prove everything, right? But yes, you'd have to prove all of this. So I will, you'd have to prove this claim. You would also prove another claim that in the BFS tree, or I should say, consider the BFS tree and let Li be the set of vertices at depth I. Okay? Then you say and consider U in Li, then all neighbors of U lie in Li minus 1, union Li plus 1. Right? This is the other claim that you'd have to prove. Excuse me. And so you would use this claim and then the previous claim to then prove these claims over here. And once you prove these claims, you can also prove this theorem. So it's a sort of chain of implications that you would build, or chain of claims, not implications, but you'd prove this, then you'd say using this claim, you can prove another claim, then using that. And finally, using all of that, you would prove this theorem, that the problem can be solved in linear time. You can also prove the theorem that G is bipartite if and only if G does not contain an odd cycle, which is a classic statement of graph theory. Okay, so with that, I'll end. I can take any questions that you have at the end. Happy to answer any questions about any of this.